I discussed a bit with Matthew, who mentioned that it would be good to give you guys an idea of um, like the game plan and where we are, why we're doing what we're doing, and where we're heading to. So here's the best, most accurate forecast I can make of like the upcoming lectures until Easter. So we spent the first couple of weeks, and you know the cap. I can imagine how all of the things you're seeing right now seem very abstract, and you would naturally ask yourself, why are we even bothering with this stuff? But hopefully, it will create a coherent picture after the course is fully developed. So what we spent our time doing in the first couple of weeks was introducing modeling issues around stochastic programs and what they actually are. Last week was about why we should even bother with solving them. And what we're entering now is the heart of the course, which is algorithms for actually tackling them. On Friday, Matthew will give you a fairly simple problem that will bring your computer to its knees, where you will see how a stochastic program can become a really difficult thing to deal with computationally. And I think that'll be a useful experience for you to see what breaks and what goes wrong, and why what we're going to learn in the next few weeks is going to be helpful for dealing with that. So we're entering the algorithms domain now, which will be mixed with some theory, so you can understand the algorithms and design new ones based on your own inspirations. So this family of algorithms that we're going to see in the next 2 weeks is very different in flavor from the L-shaped method that's addressed in the book. So we're going to look first at Lagrange relaxation algorithms. Some of the theory, however, that you will pick up here in the next 2 weeks will be used also in the L-shaped method. In particular, subgradients will be the key concept that you will be reusing, and it's important to get accustomed with it. So then week 8, so 3 weeks from now, week 6, which is 3 weeks from now, we'll look at the L-shaped method for 2 weeks, and then variants of that for the next 4 weeks that will culminate in the stochastic dual dynamic programming algorithm. And the best guess I can make right now about your course project is that it will be based on a stochastic dual dynamic programming algorithm. In particular, I have an idea about the project of, and I will be entirely honest here, I'm throwing at you an idea that I was thinking of doing during my PhD and my postdoc, and I didn't have time to do it, but I thought it was an interesting idea. I won't give you the full-blown problem, but it's fairly a manageable instance, and we can see how far we can get along with it, since I myself haven't ever tried it before. The big picture with the problem is that you have a network. Electric cars became really popular a couple of years ago. Back in California, there was a company called Better Place that had a really revolutionary idea for bringing in the network, and there was a lot of activity in Europe. So the big idea about electric cars was that you would use them as a way to replace gasoline with wind in the transportation sector. And the way that works is that you use wind power to charge electric vehicles, because they're very flexible about when they charge, what hour of the day. So instead of having a bunch of cars running in the roads and polluting with gasoline, you have a bunch of electric cars that are charged in the network from wind. The problem with wind is it's randomly unavailable. But the good thing about electric cars is that they're very flexible about when you charge. As a stochastic program now, from the point of view of the operator, my stochastic resource is wind and a bunch of other generators that I can control. And I have a multi-stage problem of decision under uncertainty, where I have a huge storage resource, electric vehicles, and I have to decide at each hour of the day whose cars to charge and how much, and how the rest of the network runs around that. So that's a naturally multi-stage stochastic program where there's uncertainty on the right-hand side, which is wind supply, and the horizon is a single day, and we're solving an operating decision problem under uncertainty of balancing the network with a lot of wind and with electric vehicles. That's the thought that I have for the project, and the underlying algorithm for tackling it will probably be based on SDDP. Now, that said, I also had promised you in the end of last lecture that we would touch on, we would cover the proofs of the bounds on the SVP. I'll do that in the end of today's lecture so that I take the main message out of the way, and then we go back to that material. So I'm going to jump straight into Lagrange relaxation, and then I'll return on SPV in the end of the lecture. Okay, so the whole idea behind Lagrange relaxation is, the whole motivation is both, it's basically, from our point of view, computational. So there are two reasons why it will be useful for us. First of all, it gives bounds on difficult problems, and second of all, it's manageable to solve. The whole philosophy of the course is you take an enormous problem, which is a full stochastic program, and cut it into pieces, and you find a disciplined way of, when you're cutting something into pieces, you're ignoring constraints. Basically, that's how you cut a big problem into pieces, by relaxing some constraints. The idea is to come up with a disciplined way of giving yourself penalties for ignoring these constraints until you eventually converge into something that is feasible. That's the big idea of what we're doing, what we're doing. So now let's try and formalize this. We start, I should also say that this material is based on Stephen Boyd's slide, and I'm pretty confident he can do a much better job in talking about it. So he also has video lectures of duality online that you can also consult if you're interested. And I find them very, very interesting and useful. So we start with a primal formulation where the objective function is f subscript 0. And we change the notation depending on whether we have inequality or equality constraints. So inequality constraints are f sub I, and there's m of them. Equality constraints are h sub I, and there's p of them. A domain of function here is the set over x where the function does not become infinite. And the domain of the whole problem is the intersection of the domains of both the objective function and the constraint functions. If we are looking out of that set, that's not a good idea, because some of these things jump to infinity, and that can only lead to bad things. Either we violate constraints, or we're not doing a good job at the optimization problem. So we have this optimization problem now, and we define a Lagrangian function based on this problem. This function is a mapping from the space of primal and dual variables to a single number. You tell me, and basically what it is a weighted average of the objective function, a linear combination, in fact, of the objective function and the inequality and equality constraints. The inequality constraints have a dual multiplier lambda I associated with them. The equality constraints have a multiplier nu I associated with it. Why do we even want to define this thing? And again, notice now that we've moved from a space of only primal variables to a space of both primal and dual variables. So why we would even want to define this is basically to move to the definition of a Lagrange dual function. So we're going to take this Lagrangian function and minimize over the domain. And this is an extremely useful function computationally. So it's defined over now only the dual space, only the lambdas and the nus. And what we're doing is we're taking the Lagrange function and minimizing over the x's. That's useful, provided we restrict the lambdas to be non-negative. Can you say something about this dual function here? You give me lambdas, you give me nus, I give you this number, and I'm claiming it's a very useful number for our problem. Why is the reason? The claim is, in fact, that any lambda, for any lambda non-negative that you give me and any nu, this number that I will return back to you is a lower bound. Here's how you can show that. So let's take some feasible x for the problem. Okay, x feasible means that the h's are all equal to 0 and the fi's are all non-negative. The Lagrangian function that I'm taking is a weighted average of this f0 plus a bunch of stuff here, and I can tell you what the sign of these things is. Because I've told you that the lambda is non-negative, and I've told you that the x is feasible. So the lambdas are, each of the lambda I fi here has to be less than or equal to 0, because when I asked you for a lambda and a nu, I told you give me a lambda that is non-negative. So this part is non-negative. If you come up with an x that is feasible, the fi is less than or equal to 0. I know that all these terms are less than or equal to 0, therefore. And because you also present to me an x tilde, but you tell me it's feasible, I also know that the hi's here have to be 0. So I got a bunch of terms here that are an f0, a bunch of non-positive stuff, and a bunch of stuff that is 0. So that's where this inequality is coming from. Now if I minimize this, then I have to come up with something that's less than or equal to the L for any given x. And that's just a definition of the dual function at that point. So I've established that the dual function is less than or equal to the objective function for any x that you present to me that is feasible. So in fact, if I'm doing my best, if I'm looking for the best x, that is also a feasible one, and therefore the dual function is a lower bound. Okay. That's already extremely useful because now we've come up with a way to bound the optimal value of the problem. So here's an example taken from Burge's book. That's from section 5.8 of Lagrange function and a dual function. So we have a two-stage stochastic program. First stage costs are f1 of x, and second stage costs are f2 of y and the outcome. Okay, and there's no dependence here on x. We have the inequality constraints here and associated dual multipliers, and this is how we form the dual function. Now, for the special case of here, by the way, notice here there's an important observation here. For a given problem, the Lagrange function and the dual function, there's not a unique one. We can decide to relax only some of the constraints. That will give us different Lagrange functions, different dual functions. So there's a lot of creativity here, and this is much of the engineering design that goes behind creating a relaxation algorithms of which functions you decide to relax. So in this case, I only end up relaxing the second stage constraints. is there, and we get this dual function here, is there a specific property that we can exploit of this dual function that can make our life easier computationally? And again, I want you to be thinking in terms of breaking up big problems into smaller sub-problems.
We can move the second term into another problem.
Come again?
We can move the second term from we're thinking about t of pi. The second term, we can remove it from the equation.
Okay.
Optimize it on another.
We can optimize the second term. Well, the second.
No, this one, the Esperance over omega of f2 of y of omega and omega.
Right.
It
Right.
just depends on y.
Right. So that basically then means that, in fact, here I haven't constructed this well, because I would also have to. I'm sorry, what I wanted to say here is basically you can relax by scenario the solution of the optimization problem and have independent problems, but in fact here the choice of x influences this part. So sorry, this relaxation that I'm showing to you is a proper relaxation, but it's not conveying the message of separability that I wanted to. I'll fix this in the slides and upload them. Sorry about that. Anyway, moving to another example of dual functions. So here's a dual function of a linear program. So this is a linear program in standard form. So what we do here is we associate with the equalities a multiplier nu, with the inequality a multiplier lambda. If you remember, we were asking for the inequality constraints to be less than or equal constraints, so we get a minus x here. And this is the Lagrange function that we obtain from that. So the dual function is minimizing this with respect to x. Now, this dual function, there's two things that could happen. What happens if this vector is non-zero? It doesn't have to be minus infinity, depending on what the sign of the entry is. So if I find any entry of here that's non-zero, since x is free to move around, I can push this dual function as low as I want, and it's still a lower bound, right? But it's not a very useful one. So I really want to be checking for dual multipliers that satisfy this equality constraint here. So when I give you a nu and a lambda that actually satisfy this as an equality, I'm only left with the term minus b transpose n. And that's the dual function of the problem. Now, one thing that is very important about dual functions is the fact that they are concave. That's very important because there are very good algorithms for solving for concave functions. And you can actually visualize how this dual function here is a concave function. It's basically a polyhedron, it's a linear function, so it's a plane defined over a polyhedron over the dual variables. And at the same time, is that clear? The geometry. So if you want to visualize it in 3D, you basically have a physical set like this, and this plane is just like defined over this physical set. So it's just this thing here, which is obviously a concave function over this set. So we know it's a concave function, and we can prove in general that dual functions are concave functions, very important for optimizing them. And at the same time, I have a guarantee based on what I said earlier that this is a lower bound. It's non-trivial lower bound because I asked you to come up with a lambda and the nu that satisfy these equalities, and all I did is I went and hit the nu that you gave me. But not only these equalities, but also I asked for you that the lambda be non-negative, and I just took a part of that vector you gave me, the nu part, I hit it with B transpose, and I can now guarantee to you that this is a lower bound. So dual functions they give you lower bounds, and they are very often non-trivial ones. And I'm going to use an example here from a project that I've been doing for GDF Suez, where in fact these guys are solving an optimization problem for a group of generating units in, I think it's Belgium, over a year. It takes about 10 hours for them to come up with a solution that they have guarantees that this solution is 1% optimal. But when you relax this problem and solve the dual function of this problem, you can come up within, I believe, half an hour to a bound it's half an hour, 20 minutes. Within half an hour to a bound that's within that same 1% that it took them 10 hours on a mixed integer linear programming solver. So often you get highly non-trivial bounds from Lagrange relaxation, and you get them much faster because the dual function is much easier to compute. Okay, so that was Lagrange functions and dual functions. Now we're going to look at the dual problems. So, right. So what I want you to think of now is what is the best bound we can get from a dual function. You tell me any lambda, that's non-negative, any nu. I do a bunch of computations, come back with a g of lambda nu, that's a lower bound. The most interesting one you can get is if you're taking this dual function and maximizing it. And that gives rise to the Lagrange dual problem. By the way, this is, if you take this idea and apply it to linear programming duality, this is the dual problem of a linear program. That's how you arrive to using the Lagrangian. The same way as in linear programming duality, you can establish relationships between the optimal value of this problem and the optimal value of a primal problem. So I'm going to denote here P star as the optimal solution to the primal problem, and D star as the optimal value to the dual problem. And we're going to use the notation that this dual vector is feasible if the lambdas are non-negative and they're in the domain of G. By being in the domain of G, I mean that we don't pick a lambda in the nu such that the dual function becomes infinite. So here's the linear program you get from taking the dual of this one over here. And the way you arrive at this is very similar to the way to the line of arguments we used over here. It's just that it's a slightly different. Sorry, no, it's the same. It's the same idea. So how did we get from here to here? This is the dual function that I got for the standard form linear program. All I need to do is bring the lambda to the right-hand side, but I've restricted you to give me a non-negative lambda. So basically saying that this holds as an equality is the same as saying this over here. Okay, so and there's a couple of statements we can make now. So one obvious statement is that the best solution to the dual problem is a lower bound for any problem to the best solution of the primal problem. for some problems, you can actually establish a stronger result that says that the best solution to the dual problem is exactly the same as the best solution to the primal problem. And that's extremely useful because often the dual problem is much easier to solve. The reason being because the dual function is a concave function, and we have a whole library of algorithms, many of which were developed by Yuri Nesterov in core for tackling dual functions.
It's true for every function?
Yes. For any primal problem, the dual, including non-convex problems, you can use very simple arguments to prove that. Basically, from the definition of convexity, you just take two trial dual feasible solutions and show that the G of their weighted average is less than or equal to the weighted average of their functional evaluation. I'm probably, if I recall correctly, I'm going to go through that proof in the next lecture. So that's extremely useful now because I can give you a ridiculously difficult, hairy primal problem, and that you at least have some hope of coming up with a really good bound. You're asking about the concavity of the dual function, right? Not about strong duality. Yeah, no, it's always concave. Strong duality, of course, does not hold in general. If it did, we would show that we can easily solve a huge class of very difficult problems. Okay. Now, there's a whole industry of mathematicians that have made it their life's purpose to come up with what they call constraint qualifications that are a bunch of conditions on the primal feasible space that make sure that your dual optimal is exactly equal to your primal optimal. I'm just going to pass you through one of the constraint qualifications called Slater's constraint qualification, but there's a whole family of other conditions. It gets really complicated. It's not going to be too useful for us in this course, but here's one that's useful to remember. Slater's constraint qualification says you give me a convex problem, so convex objective, convex constraints, and provided there's a point in the strict interior of the feasible space, the primal optimal and dual optimal value are the same. Strict interior means that I can express well, geometrically it's kind of obvious. So in this particular case here, I can find an x where the fi at that x evaluates to something that's strictly less than 0. Applying that to linear program, we have this dual function. What does Slater say here? It says that if the A and the B, if the A matrix and the B vector are such that AX, there exists some X such that AX less than B, strictly less than B, then I know that the optimal solution of the dual of this problem is the objective function value is equal to the objective function value of the primal optimal solution. Did I need Slater to even say that? You sure?
Slater. We already heard about Slater in optimization.
But did I, for the specific case, do you need Slater to guarantee this equality? Not for LPs. It's good if you know it. It helps because then you immediately can conclude it. But you didn't need Slater to hold here to guarantee the equality of the primal and the dual optimal values. We know in general for LPs that strong duality holds. Okay. Here's now a set of conditions for optimality. So suppose I tell you that strong duality does hold for a problem. Then I immediately know that the I present to you a primal optimal solution, a dual optimal solution. Because I just told you strong duality holds, I know that F0 for that X optimal is equal to G for lambda optimal, nu optimal. By definition, I know that the dual function at those dual multipliers is the best I can do with respect to X, given this input lambda star and nu star. That's just the definition of the dual function. So since I'm doing my best here, it's definitely a lower bound for any feasible X, including X star. And since I do know that the dual multipliers that I offered to you are dual optimal, they're also dual feasible, so I therefore know that the lambda stars are non-negative. So these terms are all non-positive, and this stuff is all zero. So this is basically F0 plus a bunch of non-positive stuff plus 0. It has to be less than or equal to F0. So all I'm doing in this side of the slides is showing that the G at that value lambda star nu star is a lower bound of F0 at X star. I kind of knew that already from the previous slides, but now because I also tell you that the primal, because I tell you that primal strong duality holds, that means that we also have this equality. So we have a sandwich here where the left-hand side is equal to the right-hand side, so everything within here is equal to each other. So this is really important information for two reasons. The first reason it's important is over here. This now holds as an equality when strict strong duality holds. What can you therefore say about X star? It has to be the X that for this input lambda star nu star is the best choice, since these two are equal to each other. And also, I can say that this sum here is exactly equal to 0. The reason for that is that if any of these guys is strictly negative, I can't make up for it with any other term in this summation. I know this whole thing has to be equal to F0 of X star. If any of these products is non-negative, these guys are all 0. All of the rest of the lambda i's and phi's are less than or equal to 0. So there's no way to make up for a strictly negative element in this summation. So I have to have that the product of lambda I and its corresponding constraint is exactly equal to 0. And that's the complementary slackness condition. This is basically saying that if a constraint is strictly is non-binding, then I know that its dual multiplier is 0, and the other way around. If I know that a dual multiplier is positive, I know that the constraint has to be non-binding. Okay, that basically gives us a lot of information now, because we know that when the KKT conditions hold, we have to have, when we know that strong duality holds, we have to have 4 groups of conditions that hold. The only one that's non-obvious here is this one. Can you identify where this one is coming from.
X minimizes N.
Right. So that's the takeaway from the first bullet here. Since I know that the x minimizes the Lagrangian for those choices of dual multipliers, it has to be the case that the gradient with respect to x of the Lagrangian vanishes at that point. So I just argued for the complementary slackness, and this forms a group of constraints that are a necessary condition for any candidate primal dual pair to satisfy optimality. So, for some problems, you can also prove that these are sufficient conditions, not only necessary. So, that includes, that includes convex problems. So, for convex problems, if I know that all my constraint functions and the objective function are convex, the KKT conditions also become sufficient. Now you can start creating a bunch of different combinations of when you have a bunch of constraint qualifications plus KKT conditions, and when that creates sufficient conditions for optimality. We won't go into detail into that, but there are more detailed arguments you can make about when KKT conditions are also sufficient for optimality. Learning how to form them is straightforward, so you just go for primal optimality, dual optimality. In this case, it's the non-negativity of the dual multiplier. So this is the KKT conditions applied to the stochastic program that we saw. And you have the complementarity with the corresponding constraints and the vanishing with respect to of the Lagrangian function with respect to the primal variables. Okay. Okay, so before I jump into this, well, no, I think I have a bit of time to go through this one. Okay, I will, this is probably an idea you've encountered a lot, yes?
Sorry, in the first slide, what does it mean, the slide A?
Yes.
What does it mean,
Oh, okay. That means complementarity. So, for example, this means that the product has to be 0. So both of them can't be non-zero at the same time. Okay. Yes?
You just say that it can't be non-zero, or
the product has to be 0.
okay. So one is a which
They can't both be non-zero at the same time. Okay. Okay, so this is probably an idea that you've come across before, that dual optimal values have sensitivity information. This idea, for example, has come in handy again for this project that we're doing for this energy company for creating good starting points for dual optimization problems. When you start interpreting things as sensitivities of perturbing constraints, you can exploit that in solution algorithms. Here I'm just going to formalize this argument of why a dual multiplier actually conveys sensitivity information. To do that, I want to define what's called the perturbed problem. So we take the original problem where we have Fi's being the equality constraints, HI's being the inequality constraints. And now I'm going to move the right-hand side from 0 to a small value u for the inequality constraints, a small value v for the equality constraints. So how does the dual function look like? Suppose I first of all, what am I doing here? I'm basically slightly changing the problem. If u is positive, I'm relaxing the constraint. If u is negative, I'm tightening it. For the case of the equality constraints, there is no direct interpretation. I mean, if you're making the right-hand side of an equality constraint higher or lower, that doesn't necessarily mean you're making the problem more difficult or not. But in any case, let's try and get the dual function of this problem. One thing that I should have mentioned earlier is that the way we set up the Lagrange, in order to remember on your own how to set up a Lagrangian function, you set it up in a way that it gives you a lower bound when you're minimizing with respect to x. So you want to be, when you're minimizing a problem, you want to be taking the signs of the dual multipliers of inequality constraints in the right direction. This is going to be extremely useful for learning how to set up decomposition algorithms on your own. So how do you set up a Lagrangian function for this problem here? Here it's kind of easy, but if I started playing around with this, changing the signs here, I would make your life complicated, but you've already seen the prototypical way of setting up the Lagrangian here. So what would it look like?
Zero is Fi minus.
Right. And the same for the equality constraints. Now you can see where this is coming from. So this is the dual function of the perturbed problem. You basically have the, when you're minimizing this with respect to x, you are capturing the original dual function over here, and the rest of the stuff just shows up as linear combinations over here. That's how the dual function of the perturbed problem comes up. And what we want to do now is basically think of expressing this now, the optimal solution, as a function of u and v. We're thinking of u and v as parameters. So how does the optimal solution of this problem vary as we're changing this input? And now we can think of a mapping in the space of u and v and how the p star evolves. What is the objective function, the optimal objective function value of this expressed as the function p star? The min of this problem here, can you write it as p star of something? At the origin. Okay, now if strong duality holds, we can establish the following lower bound over here. So this function of these two perturbations is lower bounded by a linear combination of the perturbations plus this constant over here. How did I conclude this? The second part is easy. This follows from strong duality. The first inequality. So I want to say that weak duality will guarantee, we have already strong duality here. Well, I want to say we have to go here and say that lambda star and nu star are just some choice of dual multipliers. They're not the best one. The best one is going to give you a value here that's p star of u comma v because of strong duality. So that's how you get the inequality here, because lambda star and nu star are just some choices of dual multipliers that are feasible. Now this has a lot of information in it. This inequality has a lot of content. First of all, one interpretation you get here is the following. If the lambda star is positive and really high, what do you know from sensitivity? Intuitively, we're going to argue sensitivity strictly right now. But when the lambda of a constraint is positive and really big, what does that imply about the problem for that constraint?
You change the constraint with a bit, but the value changes.
You get a lot of gains, yeah. And you can see that here. So if the penalty, if the sensitivity of that constraint is really high and positive, and you tighten it, so you make this UI slightly, you make the right-hand side slightly negative, this lower bound jumps a lot. So you're already getting information about sensitivity of T star of u globally. So if you want to think geometrically here, you can think that you are in the UV space, and you have this function, well, the origin is the optimal point, and we have this function p star of uv. So we've kind of like established a lower bound for any arbitrary u comma v that we pick, and it's kind of like lower bounded by this hyperplane of u and v that we have over here. That's what's going on geometrically. Now we're going to zero in on the sensitivity of this function around the origin. And we're going to say something much more specific. So what we're going to say about the sensitivity of this function around the origin is that lambda I star, the partial derivative with respect to this change in the right-hand side is exactly equal to minus lambda I star. And to show this, what we're going to do is the following. So forget all other coordinates, let's put them to 0, and let's just focus on slightly perturbing the UI. We know from this inequality that if I put all other coordinates 0 and I just move UI a bit, I'm left with, and so what we're going to do is we're going to take the U vector like this. So all of this stuff is just going to leave me with this value here. So if I move the g to the right-hand side and divide by the t over here, and then I take the limit of t as it goes to 0, provided that t is positive, that will give me the partial differential with respect to the coordinate ui. So that way I can show that this partial differential here is greater than or equal to minus the lambda star I. I can play that same game by moving t to 0 from the opposite direction, and that will give me an inequality in the other direction. And that way I exactly establish an inequality that the partial differential of the objective function value with respect to a slight change in the right-hand side is equal to minus lambda star I. Note that it's a minus sign here. Now, it'll be really useful for you later in the course to understand what ample is reporting as sensitivity. When you invoke the dot dual command in ample, it's always going to be giving you sensitivity information. So here, this lambda star is the opposite of sensitivity. It's minus the partial derivative. That's just because of the way I set up my Lagrangian function. If I had set it up with taking these inequalities in a different direction, then the lambda star would have had the opposite sign. So, the fact that I'm getting the minus lambda star here shouldn't worry you too much. You should just be aware that ample always reports sensitivity of the objective function. The reason I think a lot of this stuff is fun is because when I did engineering, I felt like I had to get creative somewhere. And when I moved from power engineering to math, it felt like all the opportunities for engineering creativity were lost. In my first year in Berkeley, for example, we were just doing a bunch of proofs and theorems, and there wasn't really this challenge of designing a system, trying different stuff, and that wouldn't work, so you had to try something else. Until I got involved with, I got a bit of that in some statistical estimation of wind production, which was trial and error. It was fun. You had the data, you were trying to replicate it with some time series model, depending on how many lags you were introducing, you were getting better or worse fits. But the part where it entered in the optimization work, beyond the statistical modeling, was the design of decomposition algorithms. So the art there is finding how to break up problems. And there are many options for taking a primal problem, rewriting it in a way that you get stupid or meaningful results. Specific things you can do to massage an optimization problem and change it a bit to say the same thing as a primal problem but give you dual function variables. There's a bunch of different things you can do. You will see some of them. An example that I mentioned earlier is to the second bullet here. Choose which constraints you want to relax. Boyd refers to that in his slides of making explicit constraints implicit. What Boyd refers to as implicit constraints are constraints you don't relax. So choosing which constraints to relax is one part of the one way you can transform a problem. You can transform the objective function. So if you have a convex optimization problem with a convex objective function, does anything change if you hit it through an increasing function? I believe not, right? You're supposing we're minimizing, for example. If we just pass the whole string, provided we're minimizing. If we pass the whole thing through an increasing function, it really doesn't change what we're trying to do. If I find the minimum of the original function f0, it's also going to be the minimum of the encompassing function phi. So we can take, for example, exponent of f0, and that creates the same optimization problem. We're really trying to achieve the same thing, but you get a different dual function. That's not something we'll be doing too much of, if at all. Introducing new variables and equality constraints, we will see an example of that in the next couple of slides. Okay, well, we will see an example here. Let's think of this problem. Minimize f0 of an affine combination of this. What is the dual function of this? As is, no constraints. You can define the Lagrange function, you can define the dual function. It doesn't have any constraints. So basically, the Lagrange function is just the objective function weighted by plus nothing. And the dual function is the minimum of this with respect to x, plus nothing, which is the primal optimal value. Nothing went wrong here. A flat level function in an empty space is still a concave dual function, as was guaranteed by the theory. We have weak duality, we also happen to have strong duality. Everything holds as it should have from the theory we saw. But it's not very, the presumption here is that since the whole motivation of relaxing this thing is because it's difficult to solve, in order to compute the dual function, I just need to solve this thing, it's a pretty useless application of the theory of duality. I really can't compute this, so it's not really useful to have the problem in this form. What I can do instead is introduce new primal variables, y, and say that, you know what, I'm going to minimize f0 of y. And what is y? It's ax plus b. And now I'm going to go and hit the y equals ax plus b constraints and get a different dual optimization problem. And that now becomes more interesting. So this is what we get when we introduce y. What's the logic behind the equality here? Can you see why this is the case? I should mention, by the way, that here we're using the conjugate function of a function, which is something that comes up in convex analysis, and it's just all you need to know is the definition of this thing. F0 star of y is called the conjugate function of F0 is equal to this thing here, over x point times x times F0 x. For some functions, their conjugate function is easy to compute, so it's useful to introduce this notion. In any case, the way we get this expression here is that if the nu that you offer to me is anything, results in A transpose nu having any component non-zero, I will take the x and take it to infinity or minus infinity, depending how I minimize my Lagrangian function. So I will get a g that is minus infinity, and that's not interesting, so I have to restrict the nu to be such that A transpose nu is exactly 0. And in that space, I get a dual function that's equal to minus the conjugate of y plus B transpose nu. That's very different and maybe easier to compute than this thing here, which is just a constant. So all we did is added new variables y, but we had the same primal problem essentially, but a very different dual problem. So you can already see how there's an art in choosing what to do. Another example is an LP with box constraints. So we have equality constraints ax equals b, and x lives within -1 and 1. Here we have lambda1 denoting the dual variables associated with these constraints, minus 1 less than or equal to x, where we take x on the other side. And we have this, and lambda 2 is this. We go through the whole construction of the Lagrange function, the dual function. We end up getting this dual problem here. So here's an example of what Boyd refers to as implicit constraints. He says, well, you know what? Suppose we only relax the equality constraints here. This is one dual problem. But you could get another one. In particular, you could get this dual problem if you're only relaxing the equality constraints. Do you remember what the one norm of the vector is? The
Sum of the values.
come again?
The sum of the two values.
Okay. So how do we get the one norm in this case here? How would you optimize so what's happening here is we're optimizing with respect to x. We factor everything that's hit by x as one single coefficient. So in this case, we have C transpose plus nu transpose A is all hitting x. So here's a vector for you. Suppose it looks like this. You want to minimize this guy, and your x has to live between -1 and 1. You're going to take it to the limit depending on whether it's negative or positive, but you're always going to be taking it to the limit. So basically what this is going to do is it's going to give you the one norm of this vector here. You want to give me a positive coefficient, I'll hit that x with -1. It's negative. And then if it's a positive one, I'm going to go take x to 1. But in the end of the day, I'm going to get the norm. So different dual function from this. And I want to now give you a more concrete example, which is also going to be much more relevant to what we're going to be doing in the homework and possibly the project also. Okay, so this problem is a stochastic program now. I haven't talked much about stochastic programming, so now I'm going to look specifically at a stochastic program. So I'm going to now show you, again, two different ways to relax the same problem with trade-offs. Let me discuss the trade-offs after we've seen the entire example. So think of a two-stage. So this is based on a paper that was written by John Birch, the guy who wrote this book, and one of his students, Survajit Sen, who's now a faculty at University of California, Los Angeles. And we have a two-stage stochastic program. We make first-stage decisions X, I, S. S indexes scenario. I indexes whether it's the first. It indexes the stage, whether it's the first or second stage. So when scenario 1 unfolds, I've made a first stage decision. It's x11. Then in the second stage, I have these two constraints that limit my second stage reaction. All of the decisions I'm making here are constrained to be binary. So what is the feasible set of first stage decisions here? Can I make a decision x11 which is 0? Does it lead to a feasible second stage reaction? if I pick my first stage decision to be 0 and the scenario 1 unfolds, I can always, so what we want to be looking, since scenario 1 unfolds, is we're now constrained by these two constraints. I can always pick my second stage decision, anything, it can be either 0 or 1, this constraint is fine. And in this case, if I pick 0, I really have to stick with 0. So if I pick 0 in the first stage, I've got to stick with 0 in the second stage. Okay. Now if I pick 1, then again I've got to stick 0, but for a different reason, because of the first constraint here. Okay, so no matter what I pick in the first stage, the second stage, x2 for scenario 1, has to be 0. Similarly, if scenario 2 unfolds, I have this set of combinations of decisions. If scenario 3 unfolds, I have these combinations of decisions. Of course, if I didn't have any second stage constraints, these sets would have 4 members each. But here I'm cutting off members depending on these linear inequalities. Clear? Or confusing? Indexing here is more important to remember. First index is stage, second index is scenario. Okay, so x1 something means first stage decision. Well, it's a two-stage stochastic program. So what has to be true for x11, x12, and x13? Assuming we first decide, then observe uncertainty. Suppose you wrote out this, and I haven't even told you the objective function yet, but it's some function. What can you already tell me is a constraint of the problem? I first decide, I then see the scenario. Suppose I write out some ample program for solving this problem, and I get x11 star equal to 1, and x12 star equal to 0. Is this a meaningful output from my model? It's like the example we had with the gambling last week. Before I see the dealer's cards, I need to make a decision. And it cannot be contingent on the dealer's cards. It has to be the same decision without knowing the scenario. So I can model this decision problem by having different indices for first stage decisions, but they have to be the same number at the end of the day. It's not a meaningful way to write out a stochastic program if they don't produce the same number. To enforce that, we have an unanticipated constraint. So what is this constraint doing?
Since they are binary values.
That's the key observation. Because they are binary.
If x11 is 1, the 2 others have to be 1.
Yes, exactly. If the problem were not a binary program, this would be wrong. This would not be the right way to model non-anticipatability. You would have to explicitly say that with different equality constraints, that each of these guys has to be equal to each other. Okay, but because the problem is binary, you can either go everybody to 0 or everybody to 1. You can't have anything complete. Okay, so here's the objective function that I promised I would give you. So it's a function of second stage decisions only, and it's just basically what you do in the second stage is your cost, and each scenario has a probability of a third of materializing. The inequality constraints I mentioned earlier. Now, what did I do here? Does this constraint look familiar? the equality in the bottom. Is the non-anticipatory constraint, the binary restrictions, and we have a stochastic program. What Matthew is going to do for you on Friday is going to take this part, and instead of 3 scenarios, he's going to give you, I don't know, like 300,000 scenarios, and it's going to collapse your machine. It's easy to construct a rich problem that can collapse your machine. The trick is to learn how to deal with it. What would you do to deal with it based on the duality ideas you saw already? Forget solving the problem, just getting bounds on the problem. Again, the idea with duality is we, unfortunately I didn't do a good idea in illustrating this last hour, but the idea with duality is we attack constraints that create dependencies, in this case among different scenarios, and we relax them and we just pay a penalty. But we attack those, what we call complicating constraints. So what is the complicating constraint here? It's the non-anticipativity. That's making my life difficult. If I didn't have to worry about non-anticipativity, I could just and I just had the rest of the problem. And this is the key observation. I could solve each scenario independently with its own local constraints. Maybe to make this more explicit, I can write out. So just take a minute. And here we also have what I could have done is taken this guy on its own, first scenario problem, this guy on its own, second scenario problem, and this guy on its own, third scenario problem. And there's absolutely no linkage among these. They have separate sets of variables. What is making my life difficult is this non-anticipativity constraint here, so I will relax it. And I will come up with a penalty for relaxing it. Which direction am I, well, okay, it's kind of obvious here. So I'm just relaxing it in the same direction that it is here. So this is the dual function that I get. I ignore the constraint, I bring it in the objective function, I pay a penalty lambda for ignoring it, and I get the dual function by doing my best given that penalty. So how do I get, for example, the first term here? And I will write something to refresh your memory. Okay, so these are the 3 sets per scenario that I have. Let's trying to understand how we got this. I'm already telling you it corresponds to these two terms here. Two things could happen, right? I can go with 0, 0, in which case this first term here is going to evaluate to 0, or I can go with 1, 0, in which case this guy becomes 2 lambda thirds, and this term vanishes. Same rationale, I compare these three candidates for these two terms here that refer to the second scenario. There are 3 candidates, actually one of the 3 is dominated by one of the other 2. That one drops off and we're left with, should I illustrate that for the second scenario or is it obvious? Obvious? Obvious, fine. Okay, dual function. What is it? Here's a question for you. Can the dual function be discontinuous in lambda? The reason being linear in general. I have said something about the dual function, although I didn't prove it. But I never said it's linear in the dual variables. It's not. This is not an LP. This is an integer program. But you yourself asked me earlier, is it the case that the dual function can be concave no matter how difficult the primal problem? And the answer is yes. We'll see that next lecture. It's concave. Can it be discontinuous? It would violate definition of concavity if it were discontinuous. I already see that it's something piecewise linear. If you actually draw it, it looks like something that drop. Okay, we have. We can already see what its inflection points are. So one inflection point is at 0. One inflection point is at 1. Sorry. Right. So one inflection point is at 0. One is at minus a third, and the other is at minus a third. So it's something that basically looks like this. Max, sorry, yeah, it's concave, excuse me. Take that back as well. Sorry. Here we started off with the maximization primal problem. So everything I showed you earlier kind of like flip sign around. So the dual function is an upper bound, not a lower bound, and it's convex, not concave. But don't worry about that. Just everything I just told you earlier flips around. So yeah, dual function is an upper bound. I know that the primal optimal value is upper bounded by this dual function. And to get the best upper bound, I'm minimizing the dual function. Okay. Turns out if you look at this thing, which you can equivalently express it as this piecewise linear function here, it's minimized at the inflection point of 0, and it evaluates to, when you're at 0, you're at this segment here, for example, and you evaluate to 2/3. And the lambda star of 0. Okay, now if you solve the primal problem, you would find that the optimal solution is to pick 1 in the first stage, and you have these second stage reactions. But the bottom point is that the primal optimal value is a third. So, do we have strong duality here? We have a gap of a third. So, what I'm going to show you now is a way to reformulate this problem and make the duality gap vanish. And that again relates to how you want to relax your problem. You get trade-offs. In general, do you like having the duality gap vanish? It's a way to solve the problem. So if you can make it vanish, fantastic news. Here's a way. I will tell you from now that with this reformulation, the duality gap will vanish. Can you tell me what I'm losing in the meantime by doing this? What did I do? And what's different from before? I'm introducing a new decision variable, y, primal. That's my first stage decision. And I'm saying that first stage decision for scenario 1 has to be y. Second stage decision for scenario 1 has to be y. First stage decision for scenario 2 has to be y, and for scenario 3 has to be y. I'm saying the same thing, right, as before. I'm just replacing the non-anticipativity constraint, the single one that we had earlier, with these guys. 3 of them, 1 for each scenario. Okay. What is bad computationally about this? And now think in terms of trying to optimize a dual function.
There's more files.
You've increased the dimension of the dual space. But the good news is that you can make the gap vanish. This is a real trade-off you have when you're deciding how to decompose a problem. You can work on a higher dimensional space and shrink the gap, or work with fewer dual variables and have a positive gap. So to see why the duality gap vanishes here, what we do is we again write the Lagrange function. We're relaxing these constraints like so. And the rest, the same for the rest of the scenario. So we're keeping this with a positive sign and bringing the x to its side. That's the constraint we're relaxing. So we get one term here that shows up for it's the lambda 1 y, and then lambda 2 y, and so on. So that's the term over here. And we have the stuff that depends on the x's. The max over 0 and lambda 1 plus lambda 2 lambda 3 is just the max of choosing between 0 and 1 over here. That's how you get this term over here. And the way we get this, for example, is the same logic. We pick among the two alternatives the best one. So we get these expressions over here. So how do we close the gap here? What would happen to the dual function if I could find lambdas such that these equalities were satisfied? Remember that g of lambda is the objective function plus lambda transpose the constraints. Suppose I discover a bunch of these guys that make you pick an x so that you satisfy this. You close the gap. If I can find lambdas that push this problem to pick x's that satisfy the constraints, the gap is closed. You can't always do that. Otherwise, there would never be a duality gap. But it gives you like a guideline of what you should attempt, how you should set the lambdas to be. So, is this clear, or did I leave you here? Not really. Not really. Okay. A dual function is defined for any lambda I like. And how do I compute it? I maximize the Lagrangian for maximization problem. Well, suppose I magically come up with a lambda where when you solve this optimization problem here, you're going to come up with the next dual, let's call it that, but I've been tricky about how I suggested my lambda to you. I suggested it to you in such a way that h of xd is equal to 0. In that case, this term basically goes away. And what you have really is a primal feasible solution. So if my lambdas push you to pick an x that satisfies the equality constraints, I've made you pick a primal feasible solution. But this is in fact a relaxation of the full optimization problem. So I've picked a lambda that makes you satisfy primal feasibility, although you're solving a relaxation of the original problem. So if it happens to also be primal feasible, then it's definitely optimal for the original problem. You can't come up with an xd that's better, that beats this, with an x that beats the xd. So if you can pick lambdas that end up satisfying the primal constraints, because the Lagrangian function is the dual function is a relaxation of the original problem, you're basically closing the gap. That's the idea here. Okay. So basically, to make that happen here, what we want to do is, for y, for example, we can pick between y of 0 and y of 1. Well, I know that in the optimal solution, we saw it earlier, the y was, the first stage decision is 1. That's the optimal decision for this problem. So if I'm going to have this achieved to make this go to 1, I basically have to have this sum of multipliers be what in sign? Sorry? When would you pick, when you're just optimizing this problem here, you would go with a y equal to 1 when I'm hitting you with something that's not negative, since you're maximizing here. Okay, so I would like that these three guys sum up to something that's not negative. Applying the same logic to these other terms here, that's one inequality that I would like my dual multipliers to satisfy. And then there's three other inequalities from these three other terms that I would like my dual multipliers to satisfy. And it's these inequalities here. So if this set is non-empty, I can come up with penalties that, although you're solving a relaxation, despite the fact that you're solving a relaxation, you'll actually end up satisfying exactly the primal constraints, provided this set is non-empty. And it turns out that in this case it is. For example, this choice of dual multipliers will urge you to pick an x that in fact satisfies the primal feasibility constraints. And once you pick that x for this dual function, which now lives in a three-dimensional space, the dual optimal value is exactly the primal optimal value. It's a third. The trade-off, however, is that how I came up with these. This is a small problem I could eyeball. I just solved this for inequalities and found one element that lives in all of them. But in general, it's hard. You actually need to come up with an optimization algorithm for the dual function. Okay, so there's, the takeaway from this example is that there's a trade-off. You can work with relaxing more constraints, but you're optimizing a dual function in a bigger space, but at least you're more likely to close the duality gap. And so, and this is a specific application in a two-stage stochastic program. Are we have 15 more minutes, right? It's 10:30. Okay. I will go through the last part of last week's lecture, which we didn't have time to cover any of the SPEV. If I have any takeaways from today's class, it's important to remember that Lagrange relaxation is a way to relax the original problem, and it's computationally makes our life easier because it gives rise to decomposable problems, and we're optimizing a concave dual function. So these are the important things to remember. Okay. Right. Okay, so going back to the EVP, I just to refresh you what we're trying to achieve from last class. We were trying to bound the wait and see solution and the value of the stochastic solution in order to avoid solving the full stochastic program. So to do that, we came up with an idea of setting up small problems where we come up with a reference scenario and we pair it up with an actual scenario from our scenario set. And that way we get to just solve stochastic programs with only 2 scenarios, but it's much easier than solving the full stochastic program. But it also gives us bounds that indicate whether it's worth solving the problem or not. That's the whole motivation behind it. The way we chose this reference scenario depended on the problem. We could take the average scenario for some problems. Typically, we want to take something that makes that is worst case, because that gives us interesting bounds. So, for example, in capacity planning problems where we need to satisfy some demand, we can take the worst case demand component-wise, and that's another good candidate reference scenario. And it may or may not be the case that the reference scenario is a member of the scenario set. If it's not, then the probability we assign to it is 0. If it is, then it's the probability of the actual scenario in the scenario set. Okay, so here's what the pair sub problem looks like. We're taking a weighted average of the cost of a reference scenario where we're assigning a weight of its probability. And then for the scenario that we're pairing it up with, we're putting the rest of the probability on that alternative. So we have first stage decisions, and again, to remind you, we're looking at 2-stage stochastic programs where there's only uncertainty in the right-hand side. And that's why we have the xi showing up here as coefficients of the right-hand side, and it's 2-stage stochastic linear programs. We use this notation over here for optimal solutions. So the y bar without a function of some xi means the y bar of the second stage reaction to the occurrence of the reference scenario. And for k means that we're looking at the kth pair sub problem. whereas y of psi k means the second stage reactions when the kth scenario occurs. So when we solve this pair subproblem, we get like this three-dimensional thing. On the one hand, we have a bunch of first stage decisions, the x bars of k. We have a bunch of second stage decisions that correspond to reference scenario occurrence. We have a bunch of second stage decisions that correspond to kth scenario occurrence. So this is kind of like a simplification really of the full optimization problem, where we're giving weight to a reference scenario and then a bunch of weight, whatever we didn't give to this guy, we give it to the scenario we're pairing it up with. It's not really the original problem, but it's something that looks like it. And this is a useful thing to solve. So suppose we solve this for all the scenarios. We collect a bunch of values z. Now we can use these values to create bounds. One thing to note, which again I insist that here you need complete recourse, but the claim in the book is that if the reference scenario does not belong in the scenario set, that means what? That the P of the reference scenario is 0, and you only have a second stage cost corresponding to that realization. First stage decisions, second stage decisions for the reference scenario and that scenario, but because you're not accounting for cost of the second stage decisions with respect to the reference scenario, it's as if you're optimizing the deterministic equivalent of this problem given that psi k occurred. So the claim in the book is that this equality holds. Of course, if this cannot be satisfied, then this equality will not hold. But in any case, assuming you have complete recourse, this holds, and you can define this number here. Again, arguably, this is an easy number to compute, because these ZPs are easy to compute. What are we doing here? We're normalizing y by the 1 minus the mass of the reference scenario, and we are averaging all scenarios except for the reference scenario. And the first thing to note is that if the reference scenario is not in the scenario set, this is exactly the wait and see value. To see this, you exploit this basically. If the reference scenario is not in the scenario set, this becomes 1 because PR is 0. Nothing is lost in the summation because all the indexes survive. And the ZPs are just the Z's of xk, so this sum is exactly the wait and see value. Okay, now you can say more. In general, you can say that the wait and see solution is upper bounded by this SPUV. So that's exactly the practical reason for bothering with this, is we want to know, is it worth solving the problem? Basically, we want to know what is the value of this guy and what is the value of this guy. And we get indications of that because it's not easy to know that a priori by computation. We get indications from the SPUV. Okay, so to show that the wait and see is upper bounded by SPUV, this is a bunch of algebra that looks complicated, but it's quite simple, in fact. This is the SPUV by definition. All I've done here is I've broken up this guy into PR times this guy plus 1 minus PR times this guy and factorized. Is that clear? This term, I've broken it up to PR times itself times 1 minus PR times itself and factorized. That's all that's happened here. And now you start playing around with the feasibility. So you know, if you keep just the part of the pair subproblem that corresponds to first stage decision and reference scenario reaction, you know that will be feasible for the deterministic equivalent problem of the reference scenario. That means you have this inequality here. Why? Because the constraints of this problem are present in this problem, but the optimal solution of this problem is not necessarily equal to this thing here. So you have this first inequality, which gives you this inequality over here. So all that's happened here is we've replaced this by the lower bound, ZR star. The rest here remains the same. We've done a bunch of simplifications. So these two guys cancel out with each other. That's why this survives on its own. Here, what happens with the sum is pretty simple. This number is equal to the sum of these, and the rest, the rest is constant, so it goes outside. So these two cancel each other, and you're left with PR ZR star. And then for the other stuff, we just keep it as it is. And really what you're left with, we don't. We bound this as well. We bound this by the optimal solution of the problem for that scenario. Recycling this argument that we already used here. Whenever you're solving a pairs subproblem, you're coming up with a feasible but not necessarily optimal solution for two different problems. The deterministic equivalent problem of that scenario and the pairs problem. That's the argument that's used in this proof over and over. Why? Because the pairs subproblem has two collections of constraints. The realization of the reference scenario and the realization of scenario K. So we're recycling that argument to basically place a bound here, and that gives us the right-hand side. So what did we do? We just upper bounded wait and see by SPV. To upper bound SPV by RP, we kind of go through the same logic, and since it's using really the same argument, just apply to the optimal solution. I think it will be easy for you to figure it out. It's not particularly, it looks hairy because of all the algebra, but once you understand this fact that by solving the pairs, you're coming up with feasible solutions for two different things, it simplifies things a lot. And then finally, the last inequality that is proven in the book that we didn't have time to cover last lecture is we come up with a bound for the value of the stochastic solution. Now, the value of the stochastic solution is redefined to correspond to the expected performance of the reference scenario. That could be the average scenario or not. But that's the generalization. If it happens that you choose the average scenario to be equal to the reference scenario, then the value of the stochastic solution as it was presented earlier in the same chapter coincides. If not, you have a generalization. So here, what we're trying to prove is we use this. We also can easily compute this number here, which this is the short name of this number. Again, the thing to note is that this is something fairly easy to calculate. So we're solving a bunch of pairs subproblems. That's how we get these x bar of k's. And then we're computing their expectation. Do you remember what it took to compute this expectation? Was it just summing up numbers? any candidate X I give you, computing its average performance for a two-stage stochastic linear program, what does it take? It's a collection of LPs, small ones. Easy, but not just, it's not completely trivial. So then we're taking the minimum of, so we have to run all these basically simulations, is what they are effectively. And we're running all these simulations, and then we're taking the minimum over all scenarios as well as the reference. And that thing we call it EP. Again, arguably something easy to compute. And then the big news in the last part of the chapter is that this thing bounds RP. This thing bounds RP, and this thing is bounded by the average performance of the reference scenario, which is a single simulation. Okay, and I think that wraps it up.